This is video 3 of our chapter 16-17 acid-base AP exam review. Let's take a look at the last free response question. I'm actually going to work both of these completely through since this is a very commonly measured concept. So we have ourselves a titration. We have 1.22 gram sample of a pure monoprotic acid, HA, that was dissolved in distilled water. And then it was titrated with some 0.250 molar sodium hydroxide, standard titration technique. Remember, titration, you have yourself an acid in a flask to which is added a base from a burette. And the base has to be strong. It's almost always sodium hydroxide. And the acid could be weak or strong. In this case, it's going to be a weak acid, as we'll see in a minute. The pH was measured throughout the titration. Notice the pH is going up, up, up as we're adding milliliters of base added. As the more we add, the higher the pH goes. And that makes sense because bases have high pHs. And the equivalence point was reached when 40 mils of the base was added. So this right here is the equivalence point. This is, of that graph that we saw, this is this point right here. The middle point, where all our acid has been titrated. That's the whole point, to get to the equivalence point. Notice the equivalence point happened at 40 mils and the pH is 8.62. So A says explain how the data in the table provides evidence that HA is a weak acid rather than a strong acid. Remember that weak acids have basic pHs. So this is basic. Weak acids have basic equivalence points. So basic. That's because HA, being a weak acid, when you neutralize HA, put OH against it, you'll actually get yourself the conjugate base. And so what you've got is, after all this is finished, after all this is titrated, you're left with a bunch of A-, which is a conjugate base. So this being a conjugate base is a weak base, which gets you pH above 7. pH is greater than 7. This says greater than 7. Good? Right, so B says write the balanced net ionic equation for the reaction that occurs. So actually I began doing that here. Now, net ionic equations, technically you got yourself HA plus sodium hydroxide. This is just a double replacement reaction. Remember, acid-base neutralization reactions as well as precipitate reactions are just double replacement reactions. So the H and Na would swap places. You get yourself NaA, and this A is just, could be fluorine, could be any big nonmetal, plus water. Now, net ionic equation means sodium is out of the picture because sodium is a spectator ion. So you end up with HA plus OH minus, giving you A minus plus water. This is the net ionic equation. No state symbols needed unless they ask for it. But recall that the stable symbols would be aqueous. For the acid, all acids are aqueous. Aqueous for the base because it's a solution of it. Aqueous for the conjugate, and water will be a liquid, which means water will not show up in the equilibrium box if we have to do it. Okay, so calculate the number of moles of HA that were titrated. Let's pull it up a bit. Now you'll see that actually the answer will come from the fact that we have added, let's take a look at this. We've added our base. We know how much of the base we added. At this point, they don't tell us how many milliliters of the acid. They tell us the grams of the acid. Well, they don't tell us the milliliters because the acid came as a dry solid. So, but we know that whatever moles of base we have, this would be moles of base, at the equivalence point, that equals moles of acid. So the whole point is you can actually use the base numbers to find out the moles of the acid that were titrated. No need to pull up. So all you have to do is get the moles of the base, 0.250 times 0.040. We can probably do this with no calculator needed, so I'm going to do 1, 2, 3, 4 to the right. So 4 times 25 gives me 100. 4 to the left, 1, 2, 3, 4. Put a 0 in here. My answer is 0.0100 moles of acid. This is the acid, which turns out to be the same as the base because we're at the equivalence points. So good? Okay, we can now get the molar mass of the acid. Molar mass, recall, is simply grams per mole. Molar mass is grams per mole. Since we have 1.22 grams of the acid that was used, and we have 0.0100 moles of the acid, we can probably do this without a calculator. This is 1/100th If you divide by 100th, you multiply by 100, which means you swing to the right twice, 122 grams per mole. So save your calculator some battery power and do this without a calculator. Then we have the equation for the dissociation of HA in water. Now we're taking a closer look at the acid, just the acid. It's shown below. Notice we have the acid plus water give us the conjugate and H3O plus. Ka is small because it's a weak acid. Assume that the initial concentration of HA before any sodium hydroxide is added is 0.200. You want the pH of the solution. We got ourselves another ice box. So anytime you have a weak acid, you have yourself. To get the pH of that weak acid, you have to use an ice box. Water we don't really care about. I just using the equation above. So we're beginning with 0.200. That's our initial. That's what the I means. That's your initial, 0.200. These are zeros to begin with. We're going to subtract x here. We're going to add x. We're going to add x. This comes out to be x. This comes out to be 0.2 minus x. Then everything is set up to equal Ka. Remember that Ka is these two divided by this one because water is out. So Ka turns out to be x squared over 0.2 minus x. And again, like before, the x can be crossed out because the Ka is 3 orders of magnitude or greater difference. So we got ourselves, let's go ahead and solve it. So we have 0.2 times our Ka, which is 6.3 e negative fifth, equals x squared. So square root this side to get rid of the x. And if you compute this, go ahead and try this. X turns out to be 0.00355 molar. That is the concentration of H plus or H3O plus because X is H3O plus. They ask for the pH. The pH is the negative log of that. So if we negative log this number here, we get a pH of 2.45. pH again has no units. So good. Hopefully this makes sense. Again, I'm going quick, so stop and think through this. Work through this on your own. The last question says, let's calculate the value of H3O plus that's left in the solution after 30 mils of the base was added. So what we have is actually we're in the buffering region of the titration, so we're roughly right here. And since we have a buffer, we have to consider both the conjugate acid and the original acid. So actually, this is the tough question. This would be like, if you remember, we did titrations all the way across, and then you can actually do, or we determined the pHs all the way across this titration, and we're going to find what the pH is roughly right here. Okay, so what we have happening during this titration, this is pH, this is milliliter base added, is we have our weak acid, HA, being reacted with our base, producing a minus and water. This is the equation actually we wrote above in part B, I believe. Now this is going to be the ICF box. If you recall, the ICF box, initial change and then the final, allows us to track the titration. So this is not an ice box, this is an actual molar solution. Or I'm sorry, this is moles of base reacting with moles of acid. The idea, if you're confused about the ICF box for now, let's think through what's happening here. We're putting the base against the acid, and we're told that we have 30 mils of the base. We know that the molarity of the base is 250, and so we can find out how many moles of the base we have, correct? That is correct. We can find out that we have ourselves, how many moles of the base? We've got ourselves 0.0075 moles of the base that we're adding. Now, the acid that we have, we figured out that we have 0.01 moles of the acid. This is kind of the weak acid, and we know this from part C above. So we've put this much base against this much acid. It turns out that all the base will be neutralized by all the acid, or vice versa, however you want to look at it. So the difference between these two will tell us that there's a little bit of weak acid left. In fact, if we do 0.01 minus 0.0075, that's how we get 0.0025. So this would be moles of acid left. And since we have moles of acid left, we'll have ourselves how much we have of the conjugate. So, because remember, anytime you got yourself a weak acid being neutralized, this is a weak acid, if you neutralized it, you form the conjugate base. So, in other words, what we've done is we've neutralized this guy, and in the meantime, we formed this guy. So actually, we also have 0.0075 moles of C base, conjugate base. So we have both of these. Now the ICF box kind of tracks that by saying, well, you got yourself 0.100 moles. That's what we said we had. This is 0.0075. I'm sorry, not 0.100 moles, 0.0100 moles. 0.01 mole, 0.0075. Essentially, I'm just reproducing these numbers right here. And the base will neutralize the acid, so we're going to subtract 0.0075. We're going to add 0.0075 here. The water doesn't matter because it's a liquid. So we essentially have, once this is said and done, 0.0025, and this is 0.0075. So we have these two amounts in solution. We have ourselves a buffer. In order to get the pH of a buffer, we have the buffer equation. Remember, pH of a buffer is negative log of Ka plus log of base over acid. Let's get the pH. They want the H3O plus. Well, we know that H3O plus is connected to pH, and the equation was 10 to the negative pH is H plus. So once we get the pH, we'll do 10 to the negative pH, and we got it. We're really close to the pH because we have these two values. Since we have these two values, backwards, acid over base, base over acid, right here. We have those two values, we can get this done. So negative log of Ka, our Ka was given to us before, so we have negative log of 5.6 E negative 10 plus log of base over acid. Our base is 0075. Our acid is 0025. And if you compute all this, we're running out of room. Go ahead and compute all this. You will get yourself a pH of 4.68. Since you know the pH is 4.68, you can now do 10 to the negative 4.68, and you'll get yourself a final concentration of 2.10 E negative 5. This is now molarity in the end. So this is the final answer. Circle it well. A bit messy. The whole point is this is the toughest, I think, of the questions. I think a tough question is to find out the pH right here, or the concentration in the pH right here. But think through it. And the whole point was we knew how much acid we began with. We added a certain amount of base, which neutralized that weak acid and formed it into its conjugate. Since we had both, this is the buffer region, remember, of the titration curve. Since we had both, we can plug that into the buffer equation, very powerful equation, and find the pH. And then we undid the pH and found our H+. Think through these questions, come with a few of your own questions, and we will see you in class.